Students who are already present, please give your attendance in the chat box. And please rename yourselves with your enrollment number. Those who are not named with your enrollment number, please rename yourself with your enrollment number. Okay, so let us start. Now, previous day we had ended our discussion on the serializability topic of transaction. So first today we'll spend some time on the transactions and then we will move to our software engineering where we will be doing some problems. Okay. So when we are into transactions, why we are behind this serializability topic, why this is important? See, when there is a concurrency, that means more than one transaction is trying to take place alongside simultaneously, then there is a question of consistency. Now, transaction must follow the property of acid property. The transaction must follow the acid property. Now, if I talk about acid property, it is atomicity, consistency, consistent. Just give me 1 second. Yes, so atomicity, consistency, isolation, and durability. Okay. Okay, can all of you see my screen? Right now I'm writing something, so can all of you see that? Okay, okay. So a transaction, some of them are saying no, majority is saying yes. I hope it is visible. Okay, just 1 second. Yes, I think this is visible. So those who are not able to see, please, you may log off and then re-log in, because I think this is visible. From my end, if I am logging in from another computer, then it is visible. Okay, so a transaction must follow the acid property: atomicity, consistency, isolation, and durability. Now, when we call for consistency, this means that even if there are more than one transaction taking place in a particular database, then the changes that are being made by multiple transactions at a time, those changes will be preserved. That means, if suppose I am deducting 10 rupees from my account, then either the 10 rupees will come out in my hand, or else it will be transferred to someone else's account, right? So there should not be any loss in between. That is consistency. So the total number of variables that are present in a particular transaction or a concurrent schedule, the sum of the values, understand what consistency means. If I have concurrency in transactions, then the values of the variables, their sum must be equal in the beginning and at the end, right? So if I have two accounts, A and B, A having 5,000 rupees and B having suppose 2,000 rupees, suppose in between some transactions happen, and finally if A is having 1,000 rupees, then B must possess 6,000 rupees. There will not be any data loss. So if they are having total 7,000 rupees at the beginning of your transaction or schedule, whatever you call, then at the end also they must possess 7,000 in any form. A can have 500 rupees, B can have 6,500 rupees. A can have, suppose A can have 5,100 rupees and B can have suppose 1,900 rupees. Any permutation, combination, any variable values, but the sum of the variables possible will always be same at the beginning and the end. This is my consistency. So if someone asks you what do you mean by consistency, you can give just simple this type of example, that the number of variables that are present in my schedule, the sum of the number of variables, means the values of those variables at the beginning and at the end must be same. In between, whatever happens, I am not bothered, but at the end, when you are committing your all transactions of your schedule, the value must be equal. Okay. Now, if I have, next is, if I have a if I have a non-serial schedule, then how does a non-serial schedule looks like? If suppose S is my schedule, T1, T2, T3 are my transactions, then suppose some instruction of T1 is executed, then some of T3 is executed, then some of T1 is executed, then some of T2 is executed, then T3 is executed, and finally T1 is executed. So if this is my pattern of execution, then we call this as my non-serial schedule. Non-serial schedule means where we have context switching. What do you mean by context switching? If there are more than one processes, one transaction is one process. What is a process? Any number of written instructions, when they are executing, they are becoming process. So if there are more than one processes and once they start executing, they do not execute one after another. That means after completion of one process, other one starts. So there are no switchovers. There are no changes of the processor who is working. Once T1 is starting, some of the executions are done and then it moves over to T3. Then T3 is done, it is moving over to T1. Then T1 is some way done, T2, then T3, and then back to T1. This type of switching, these type of changing of processes are named as context switching. Fine. Now, if context switching is present in your schedule, we call that as non-serial schedule. But as you can see, there are many switchovers. We cannot guarantee. We cannot guarantee the consistency property of the transaction. Right? So what we do? What do? We try to follow a serial schedule. We try to follow a serial schedule where if it is my S, it is my T1, T2 and T3, then T1 is totally done, then T3 is totally done, then T2 will be totally done. This will be my serial scheduling where one transaction is working. Once that transaction is totally done, then only the next transaction will start. Next can be anyone, T2 or T3. Serial schedule does not mean T1, then T2, then T3. That order may not be same, but when one transaction is starting, that transaction must finish. Then only the next one will start. Right? I hope you are understanding. So this is your serial schedule. Fine. So from a given non-serial schedule like this, how can I convert it to a serial schedule? When a non-serial schedule is given, my consistency is at a question mark, right? But I cannot do that. Consistency must be assured by the acid property of transaction. So what I have to do? I have to go stepwise, one after the other. That means any non-serial schedule must be converted to a serial schedule in order to assure the consistency. This line is very important. Any non-serial schedule given must be converted to a serial schedule in order to assure the consistency. Right? So up to this is fine. Now, how this conversion will be done? How this non-serial to serial schedule conversion will be done? Now, for this, we have found out the term serializability. What is it? Any non-serial schedule given to you, any non-serial schedule given to you, if you are able to find out an equivalent serial schedule, then we call that this non-serial schedule is serializable. If you find out an equivalent serial schedule, then you will say that this non-serial schedule is serializable. That means you can convert it to a serial schedule. And if it is serializable, then only it can assure your consistency. Right? So the process by which you are converting or you are trying to test whether it is serializable or not, that process is named as serializability. Okay, so what is serializable? Any non-serial schedule for which I can convert it to an equivalent serial schedule, that is serializable. The process by which you are doing this conversion or testing, whatever, is named as serializability. Fine. Next, we have two types of serializability check. We have two types of serializability check. One is conflict serializability, which is easier to check, and one is view serializability, which is a bit difficult and confusing to check, but we will study. Fine. So conflict serializability and view serializability, right? When we talk about conflict serializability, what do? We try to find out non-conflicting instructions from a transaction. And then by swapping them, we try to evaluate a serial schedule. Understand with example. We are now discussing on conflict serializability. After that, we will discuss on view. Transaction TI, transaction TJ. Two transactions I have. Transaction TI is having instruction II, and this is having instruction IJ, right? I have to find out whether II and IJ, these two are conflicting or not. Whether they are conflicting or not. If they are conflicting, then we cannot evolve an serialized schedule, serial equivalent schedule. We cannot form. If they are non-conflicting, then we can do something, right? So let us first test that how we can say or how we can conclude whether they are conflicting or not. II and IJ. Please understand, if in one transaction I have II and IX, these two will not be swapped. Within one transaction, two instructions will not be swapped. Within two transactions, the instructions that you have, if they are non-conflicting, then only they will be swapped, right? So within the two transactions, the swapping will be done. Within one transaction, different swapping cannot be done. Within one transaction, the order that is given, that must be maintained. Between two transactions, I can do some swapping, right? So how I will do the swapping, that I am demonstrating right now. Now see, II and IJ. If I have read A and write B, read A and write B. So what do you mean by swapping? Swapping means if I do a swap, then the work, the timestamp of this will be done first, and then this. This is what a swapping means. This one's working will be done first, and this one's working will be done next. This is swapping. So this timestamp will be occupied by the next one, and this one's timestamp will be occupied by the previous one. This is what a swapping means. So if I do a swap, this is what my result will look like, right? So can I do a swap? Can I swap? How do I know I can swap or not? If they are non-conflicting, then only I can swap. So read A versus write B. See, how can I say that they are non-conflicting and I can swap? If there is any dependency, understand, if there is any dependency, then we cannot swap, or we cannot do a comment that they are non-conflicting. If there is dependency, there will be conflict. But here you see RA and WB both are working on different data items. both are working on different data items. So if both are working on different data items, A and B, there is no dependency. If they are working on different data items, then do they depend on themselves? No. If they are working on same data item, then only they will depend. Suppose you are sharing a book, you and your friend are sharing a book. Then the order of the book reading, suppose you are reading first, then your friend is reading. Now, when you are reading, if you tear some pages, suppose you are tearing off some pages, when your friend is reading, the friend will know that there are no pages like this, right? Because they are already teared off. But if I swap, means if your friend is studying fast, the friend will get all the pages. And when you are studying back, you are also getting all the pages because your friend is not doing anything with the book. So what it means? The ordering of the book reading, the content is mattering because two different persons are sharing, right? So suppose some people are having the habit of highlighting things, right? So suppose your friend is highlighting some pages and you are having difficulty to read when you are reading it later, right? So when you are doing something on the book, we call it as the write operation. You are making changes, so that is write operation. So when both of you are reading different books, suppose you are reading a book of DBMS and your friend is reading a book of data structure. So there is no problem because you are not sharing anything. So whatever you do with the book does not matter. You are not dependent. But when after you finish your book of DBMS, your friend will read, at that point of time, those tearing of pages, making changes in the book will matter, right? Because you are sharing that data item. Similar thing applies here. If the data item is different, then there is no question of conflict, there is no question of dependency, right? So in this case, if this is my scenario where two different data items are working, so we will say they are non-conflicting instruction, right? They are non-conflicting instructions. This is my scenario number 1. Next, II and IJ. If suppose it is reading A and this is also reading A. So data item is common. Right? So II means you are reading a book and your friend is also reading a book, but no one is making any change. Write A is not present. WA is not present. So none of you are changing anything in the book. That means what? They are also non-conflicting. If you are sharing a data item, but you are not making any changes to that data item, that means you are not writing anything, that means that it is non-conflicting instruction. So read A, even if they are same data item, then also that is non-conflicting. Now, case number 3. II and IJ, this is doing read A, this is doing write A. Now the problem will arise. Suppose the value of A colon equals to means temporary value is 10. Write A means some changes will happen, so it is becoming 15. Right? Now if you swap, that means write A is done first and then read A is doing. So here my A is becoming 15, write A. Then when it is reading, it will get the value of A is 15. So see, the value of A is 15 here and the value of A is 10 here. That means what? The work that is being done on the different schedules. This is one schedule. This is my S schedule. This is my S1 suppose schedule. So the order of working is making changes to the variables. The order of working is making changes to the variables whenever any one of the instruction is right. At least any one of the instruction is right. Then it will always be conflicting in nature. It will always be conflicting on nature, right? Similar applies if you have write a here and read a here. Any one of the instruction is right instruction sharing a common data item will always conflict. Right? Right? So for constraints and the constraints that you are having, if you evolve with, suppose, now what are the points that we can jot down? A non-serial schedule has to be converted into an equivalent serial schedule by, how do we do this? By swapping of non-conflicting instructions, right? So this is my agenda point. How do I convert? If I have non-conflicting instructions, then I can swap them and convert it to a serial schedule, right? Now, how to find out whether non-conflicting instructions are present? The first point, instructions from different transactions can be swapped if they are non-conflicting. Same transaction, if you have a common transaction, then within a common transaction, the instructions that are present, you cannot swap them. Okay, they must be in order. So different transaction, if they are having non-conflicting instructions, then you can swap. How to find out non-conflicting instruction? How to find out? Sharing of a common data item. Non-conflicting means sharing a common data item and no right instruction. If they are sharing data items and none of them are right instructions, then they are non-conflicting. Or if they are not sharing any data item, and executing any instructions, then they are non-conflicting, right? So how do we judge whether the instructions are non-conflicting? Either they are not sharing any data item, then they are non-conflicting. If they are sharing a data item, then if anyone, at least anyone is a right instruction, then they are conflicting. Okay, so if there are no right operations, then they are non-conflicting, right? So how case 4 is conflicting? Suppose this is, so this has to be reading it as 15. Now if you swap them, read A is being done first, and then here my write A will be done. Suppose this read A is doing what? This is reading some previously written value. So suppose this is reading it as 100. And when this write A is coming, this write A is writing the value of A is equals to 10. So this reading of 100 is done because before this, some other transaction may have written some value on A, right? So you can see the read value is not same. Fine. So this is a conflicting instruction. Okay. Another last case where both are right. Case number 5, you can say II and IJ. Suppose this is also writing, this is also writing, sharing common data item, and at least one is right. Here see both are right. Right. So what it means, this is a type of blind write. Yes, previous day we have studied what are blind write. Blind write means writing without reading. That is blind write. So suppose this is changing the data item A as 15 and this is changing the data item as 20. If you swap them, then this is writing first. Suppose this is making this as 20 and this is making this as 15. So see the order of data change. The value of A is changing here in this S. It is changing as 15 and then after that 20. So final value is 20. But here in S1, if I swap them, then the final value of A is remaining as 15. That means there is a problem. So if both are also right, then also conflict happens. So to avoid conflict, that is non-conflicting instructions, either you execute on different data items, then they are non-conflicting. If they are working on same data item, then both of the instructions, if both are read, then also they are non-conflicting. Even if one instruction among the two are right, then conflict occurs. You cannot swap them. You cannot swap them. Right? So these are your points by which you can judge this swapping. Right? Now, next we will use some problems to do this. Okay, what are the problems that can be asked? Suppose I have S1, I have T1 and T2, right? So T1 is read of A, write of A, read of B, write of B, read of B, write of B, read of A, and write of A. Okay, so this is my schedule given. Right, so this is my schedule given. Now I have to judge that whether a non-conflicting instruction swap can be done, which will lead to producing a serial schedule. Now this one is a non-serial schedule. You can see context switching is happening. T1 is doing something, then T2 is doing something. Again, T1 is doing something, T2 is doing something. So which instructions I can swap? This set with this set. Same transaction, different instructions, I cannot swap them. Similarly, this one to this one, I cannot do a swap because same transactions. So what I will do? I will try to swap this intermediate one to this one. Means what? This will go here and this will come here. No. No. So what will happen? By swapping, what will happen? This will go in the timestamp of this one. That means in this place, it will reside. And this will come in the timestamp of this one, that is this place, right? Can we do this? This is our question. Understand. What do we mean by swapping of instructions? This one is working in this timestamp where T1 is not doing anything. And this instruction is working where T2 is not doing anything. So what is my goal? My goal is if I can shift this one up in this vacant place of T1, and if I can shift this one down in the vacant place of T2, so that the total block of T1 will be done first and the total block of T2 will be done next. So what I mean, I want to evolve a T dash where my T1 and T2 will be doing like this. Then this one will work. Right? So from this, if I swap the instructions and I can evolve this one, if I can evolve this one, then I can say this is a serial one, right? So whether I am allowed to do this or not, this is my question. Whether I am allowed to do this or not, this is my question. Can I do this? Can I do this? See, this is RB, this is WB. This is RB, this is WB. I have to check between these two sets to find out the non-conflicting instructions, right? So what is my rule? If they are having common data item, like here they are working, both of them are working on B. Both of them are working on B. So B is my common data item. So if there is any read and write instruction, then only swapping will not be done, conflict will occur. So see, read B, here I have read B, I don't have any problem. But with this read B, when I do the write B, then only problem occurs. This is having a read B, this is having a write B. So there is a conflict, right? This is having read B, this is having write B. Again, this is having write B, this is having read B and write B. So problem will occur. I cannot swap them. They are conflicting instructions. I cannot swap them. They are conflicting instruction. So this one I cannot deduce. It cannot be converted to a serial schedule. Okay, it cannot be converted to a serial schedule. If my situation is like this, my S is having T1 and T2, where T1 is having read A, write A, T2 is having read A, write A, T1 is having read B, write B, and this is having read B, write B. Now you tell me whether can I do the swapping or not. Can I do the swapping now? Whom I have to swap? This set. So they are working on different data item. Different data item. Right? They are working on different data item, A and B. T2 is working on A and T1 is working on B. That means what? If there are different data items, then there is no question of conflict. There is no question of conflict. So I can declare that they are non-conflicting instructions and I can do a swap. So after I do a swap, what I will get? What I will get? This will go up and this will come down. That is what your swap will do. So if you have T1 and T2, then after swapping, it will be RA, WA, RB, WB. After that, Here you have RA, WA, RB and WP, right? So from this, after swapping of non-conflicting instructions, I will get this serial schedule. That means this non-serial schedule is conflict serializable. So my answer is this non-serial schedule is conflict serializable, right? Why? Because I have been proved that it can be converted to a serial schedule by swapping of non-conflicting instructions, right? So first T1 is done and then T2 is done, right? Up to this is clear. Is it clear? What is non-conflicting instructions? How can I do a swap? Why even we are doing the swap or converting it to a serial schedule? Is this much clear to everyone? এই অবধি বুঝেছো সবাই? Those who are attending, please answer whether you have understood up to this or not. Have you understood up to this? Okay, last one. Yes, I'm just doing with the last one. Here you see AC is having T1 and T2. AC is, T1 is having read A, write A, read B, write B. And T2 is also having read A, write A, read B, write B. Fine. Now, if I want to convert it to a serial schedule, this is a non-serial one, right? This is a non-serial one. So if I want to convert it to a serial schedule, then what I have to do? I have to make it some swaps. So where I will do the swap? This particular zone where T2 is being done first and then T1 is being done first, if I can change the order of working, that is T1 is done first in the vacant position of this T2 was working and this one will be done here. If I can do this, then I can convert it to this particular schedule. This particular schedule, RBWB has gone up. See, RBWB has gone up, right? So how can I say I can do this swapping? This total set, whether this total set is non-conflicting or not, I have to find that out. How to find out? I have to check the data items at first. See here, the data items that are working are different for different transactions. T2 is working on A and T1 is working on B. What it means? Both of them are working on different mutually exclusive data items. So if they are not sharing any data item, there is no dependency. Even if you do data change in T2, that is A, then T1 is working on B. So there is no dependency, right? So I can say that this total set is non-conflicting in nature because they are working on different data items, right? So if they are working on different data items, then I can swap their timelines. So if I can swap their timelines, then this can be done first, then this can be done. So if it is done like this, then this particular schedule is evolved, right? Sorry. So if it is evolved, then I can say that this non-serial schedule can be evolved with this serial schedule. If so, then the non-serial schedule is conflict serializable, right? Are you getting this now? Have you understood? If they are working on different data items, we can do any type of swapping. If they are working on same data items, if both are read instructions, then also we can do swapping. But in the first example, as They are working on same data items. As they were working on same data items, so we could not swap, right? If they are working on same data items and read write operations both are mixed, so we cannot do the swap. No, we are not doing the swapping to reduce time. No, we are not doing it. We are swapping to ensure consistency. One transaction is totally done, then the next one is working. If I can ensure this, then I can ensure the consistency. One after the other, if I am doing, then consistency is maintained. If there are context switching, then there can be problems. So we are avoiding non-serial schedule. We are going with serial schedule. Okay. Next one. Now there is another problem. Problem is this: if you have a schedule where you are having T1 and T2, right? A non-serial one. Then if you convert it to a serial schedule, then either first T1 will be done, then your T2 will be done. This is one way. Or first your T2 will be done and then your T1 will be done. These two ways of serial schedule I can produce. Serial means what? One after other. So here T2 follows T1 and here T1 follows T2. Fine. So if I have two transactions, then how many serial schedules we are getting? 2. That is 2 factorial. Right? How can I say this? If I have 3 transactions, if I have in a non-serial schedule, if this is a non-serial schedule, then in a serial schedule, how many options I will get? T1 is done, then T2 is done, then T3 is done. T1 is done, then T3 is done, then T2 is done. T2 is done, then T1 is done, then T3 is done. T2 is done, then T3 is done, then T1 is done. T3 is done, then T2, then T1. T3 is done, then T1, then T2. These many options I can get if I follow a serial schedule. So what is it? 3 factorial, that is 6. 6 options. How you can arrange the serial schedule? There are 6 options, right? So now you see, if you are following this approach, that you find out which ones are non-conflicting, then you arrange them and find out a serial schedule. If you follow this approach, then for one schedule given, you have to test for all 6. You have to test for all 6. So this is very time consuming, right? You have to give many effort. If you have 3 transactions in a non-serial schedule, then when you try to convert them in a serial schedule, you have to try 6 combinations. So this is hectic. After you try all 6 combinations, then only you can say that yes, serial scheduling is possible, or else no. So to avoid this problem, we take a shortcut and we call that as precedence graph. For a non-serial schedule given, we will draw a precedence graph, and looking at the precedence graph, we will take the decision that whether it is serializable or not, whether it is conflict serializable or not. So test of conflict serializability. right? So let us take a schedule. T1, T2, T3. Right? R of X R of Z, W of Z. Okay. R of Y. Suppose W of Y. So I'm taking the example from a book only so that there is no further confusion. Okay, so see here. This is my non-serial schedule given. Sorry. This is my non-serial schedule given. Now what I will do, I will draw the precedence graph. How to draw the precedence graph? The first point, number of transactions present in the precedence graph, they will be the number of nodes. Right? Fine. Point number one, easy. Next. Okay, one more thing, you can draw the lines to find out the difference between the timestamp. Which one is done, sorry, which one is done first and which one is done later. To distinguish that, you can draw some lines. Okay. If you are confused, please draw lines and then only work. Okay. And this one is the last one. So, fine. So how we will now draw the edges. This is a graph. Graph means set of nodes and edges, vertices and edges. So vertices I have drawn. Number of transactions are the number of vertices. Next, how the edges will be done? I will start from top to bottom. The approach is top to bottom, right? Look at the schedule given from top to bottom. Take the first instruction and check on the other transactions at the bottom whether you have any conflict or not. Means this is my read on X instruction, R of X. R of X will conflict with whom? W of X. R of X can conflict with only W of X. R of X cannot conflict with R of X again, because read instruction with another read instruction will not conflict, right? So R of X will only conflict with W of X, R of Y, W of Y, R of Z, W of Z. With these instructions, they will not conflict because different data items. So what I am trying to say, if you have R of X, R of X will conflict only with W of X, right? So it will conflict. If you have R of X and you have R of Y, W of Y, R of Z, W of Z, then they are working on different data items. They are working on different data items. So conflict will not occur. So if you have R of X and in any other transaction, if you have W of X, then only your conflict will occur. Okay. If conflict occurs, then you will draw an directed edge from the previous one to the next one, right? So first you understand R of X will be conflicting with only W of X. Up to this is clear. Now I will try to find out after R of X in this schedule, after R of X, Is there any W of X in any other transaction? See, after this line, whether there are any W of X in T2 and T3. T1 I will not see, because within one transaction there will not be any conflict. Conflict will always be one transaction to the other, right? So R of X is having, T1 is having R of X and T3 is having W of X. So this one to this one may be a conflict when you swap, right? So T1 will have a directed edge on T3. T1 will have a directed edge on T3. Okay. Next is R of Z. Next timeline is R of Z. So next is R of Z. So R of Z will conflict with only W of Z. R of Z will only conflict with W of Z, right? So is there any W of Z in T1 and T2? Yes, this one will conflict with this one. So T3 to T2, directed edge. Next, W of Z of T3 will again have a collision with this one, but already I have drawn one line, one directed edge. So multiple lines on the same one are not required. Next, T2 is having R of Y. Okay, so which one it will conflict with? W of Y. So is there any W of Y present in T1 and T3? No. So there will not be any conflict. Next, R of Y of T1. This one will conflict with W of Y because this is in T2. So T1 to T2. Okay. Next, this W of Y. This W of Y will be conflicting with anyone from T1 and T3. W of Y will have a conflict with R of Y and W of Y, but none of them are present in T1 and T3, right? Next, W of X. This W of X will conflict here. This W of X will be conflicting here with T1. So T3 to T1. T3 to T1, right? T3 to T1. And the last one, next one, I have WZ here, I have WZ here, but after that there are no WZ in T1 and T3. Similar, W of X of T1 is the last instruction, so it will not collide with anyone, right? So this one is my precedence graph. This one is my precedence graph. So how I have drawn? First, I have drawn all the possible nodes. That is, the transactions are your number of nodes. So T1, T2, T3 I have drawn. Next, the instructions I will start from the beginning, and then with each timeline. Suppose if you start here and then you jump here, and these particular ones you miss, then it will not happen. So this one, then this one, then this one, then this one, then this one. Likewise, order you have to follow. And any instruction which is having any conflict or not, this you will check always downwards and with other transactions. So if you are checking one instruction of T1, then you have to check it with T2 and T3. Okay. So likewise, I have forwarded and I have got this particular graph. Now, next, if any cycle is formed, then the non-serial schedule is not conflict serializable. If any cycle is formed, in the graph that you have drawn, then the non-serial schedule from which you have derived the graph, that schedule is not serializable. Okay, and if there is no cycle formed, if no cycle formed, then serializable. Okay, so here in this one you see T1 and T3 are making a cycle. T1 and T3, T1 to T3, then T3 to T1. Cycle does not mean that all vertex will be included. Cycle does not mean that all vertex will be included. Within a graph, less than the total number of vertex also cycle can be made. Any cycle, I have told the term any cycle. So if any cycle is made, then only then and there I will say that no serializability can be obtained, right? So here you can see T1 and T3 are making cycle. So if they are making cycle, then loud and clear, not serializability cannot be achieved. Now you can ask why. Now you can ask why. How you are saying this? Apply your common sense. What this cycle means? This cycle means T1 is dependent upon T3, right? Because T3 to T1 is an arrow, and T3 is dependent upon T1 because T1 to T3 is an arrow. That means T1 and T3, which one is depending upon which one, we are not sure, right? So that the cycle has formed. So which one will be executed? Can I do T1, then T2, then T3? Can I do T1, then T3, then T2? Which one, which order I will follow? Will T1 be executed first, then T3 be executed, or first T3 is executed, then T1 is executed? This answer is not clear because cycle has formed, right? So we will say that if any cycle is formed, then the serializability is not achieved. So if cycle is formed, then the schedule is not conflict serializable. Okay, not conflict serializable. Now see, there will not be any self loops. Like if I say that T2 on T2, this will not be never be happening because within one transaction, how an arrow is being formed in this precedence graph? How an arrow is being formed? If this one is checked with this one, then only the arrow can be formed, this to this. But within one transaction, we will not check the conflict. Within one transaction, we will never check the conflict. Okay, so arrow will only be formed between transactions, not on a single transaction. No self loops will appear. No self loops will appear. Okay. Yes, cycle. If a cycle is not formed, then only serializability can be achieved. If a cycle is formed, then serializability cannot be achieved. T3 to T1, how it is possible? See, in T3 you have WX and in T1 you have WX. So T3 to T1 conflict is occurring. So T3 to T1 I have put in that arrow. Clear? Is it clear? This precedence graph is clear to everyone? Yes or no? Self loop, I am telling that in some of the cases we are finding that students are creating self loop in precedence graph. That is never possible. Why? How can you draw a self loop? Suppose you have a node T2 and you are creating a self loop. What it means? One transaction of T2, one instruction of T2 is conflicting with another instruction of T2, right? Then only I can create an edge. Fine. But here in case of transactions, within transaction, multiple instruction cannot be taken for your swapping. Within one transaction, multiple instructions cannot be swapped. So we will never check for within one transaction whether there can be any conflict or not. That is never possible. Okay. So self loops are not possible. Okay, this question is clear. This question is clear so that we can proceed toward the next one. Okay, so we will do the next one. So we'll take another example where we will find out that this is your question number 2. So the previous one, let me write it as question number 1. Question number 1. Okay. So here, let us take one. So the previous one, it is not serializable. So let us take in this one, it is serializable. Okay, then we will decide the order for which we are learning the precedence graph. Okay, R of X, R of Y, R of Y. W of Y, W of X, W of X, okay, so let us start. T1, T2, T3. Fine. Let us start with T1, R of X. So we will find W of X in T2 and T3. In T2, I have W of X. And in T3, I have, in T3, I have W of X. And in T2 also, I have W of X. So T1 to T3, T1 to T2. Okay. Next one. R of Y. So R of Y will conflict with W of Y. So after this, do I have any W of Y in T1 and T3? No. So this will not do any conflict. Then this one. T3 is having R of Y and this one is having W of Y. So T3 to T2. Okay. Next, W of Y. W of Y will conflict with R of Y and W of Y. So here I don't have anyone, so no conflict. This one will conflict with this one and this one. So T1 to T3, T1 to T2, T1 to T3 already done, T1 to T2 already done. So no conflict. Next, T3 is having W of X, T2 is having W of X, R of X, both. So T3 to T2, so T3 to T2 already done. So all edges are done. Now see whether there is any cycle. No. No cycle. That means it is conflict serializable. So no cycle form. That means it is conflict serializable. Now what I have to do, I have to find out if it is serializable. That means what? Again, 3 factorial combinations of serial schedule. But I need to avoid that, right? I need to avoid that so that I am learning precedence graph. So how I will avoid that? I will be finding the perfect order of the serial schedule. So if I want to have a serial schedule, I will look at the graph and find out the vertex with no incoming edge, means no dependency. The vertex with no incoming edge will be the start point. The vertex with no incoming edge will be my starting point. Next, the vertex with no, let me write, no outgoing edge. No outgoing edge will be the end point of my serial schedule. And the vertex left means remaining will be done intermediate. Okay, will be done intermediate. So if you look into this graph, which vertex is being having no incoming edges? T1 is not having no incoming edge, right? Who is having no outgoing edge? This one, no outgoing edge. So only one is remaining, that is T3, that will be done in the middle. So T1, then T2, sorry, the T1 and T2 at the beginning, at the end, and the intermediate one is in the middle. So this is my order of the serial schedule. T1, then T3, then T2. This will be my order of the serial schedule. Okay. So after drawing the precedence graph, if these conditions are possible, that there are vertices with no incoming edge, then we will be starting from that vertex because no dependency is there. If there is any vertex which is having all incoming edges only, no outgoing edge, then that will be done at the last. Okay. And if there is any intermediate vertex which is having incoming and outgoing edge both, then that will be done in between, right? So this is how we can find out. So 3 factorial number of serial schedules. We don't have to draw and verify which one is correct. From precedence graph, we can directly derive that which after which will happen. Okay, is it clear? Is it clear to everyone? Yes, whenever no cycles are formed, then only serial schedule can be produced. Then only you need the order. If cycle is formed, there is no question of serial scheduling. Then why did you need schedule means order? Okay, only if no cycles are being formed, then only you require the order of serial scheduling, right? Fine. So drawing a precedence graph and deriving all this is clear. Okay. Okay, so next we will take another example. Another type rather, where something very interesting will happen. Let us see. Let me just extend this page so that I can complete the conflict serializability within this page only. Just wait for a minute. Okay. So question number 3, suppose S, T1, T2, T3. Suppose this is my scenario. Okay. I will draw the precedence graph to check. Okay, now you tell me that from which edge, which vertex to which vertex should I draw an arrow? Check and tell me in the chat box. From which vertex to which vertex should I draw an arrow? Tell me. I need some answers. Okay, so some students are saying we cannot draw any arrow. And one student has told that T1 to T2. So let me just check. This is your A, right? This is not B. B bhabcho, this is A. Okay, so RA will conflict with W of A. So is W of A present in T2 and T3? No. Done. R of B. So W of B is present in T1 and T3? No. T3 is working on C. So C is not being used in T1 and T2. So fine, no arrow. T2 is working on WB. So again, no RB, WB is present. So T1 is working exclusively on A, T2 is working exclusively on B, and T3 is working exclusively on C. That means there is no point of any dependency. There is no point of any dependency. So I cannot draw any edges on my precedence graph. Right? So first point, no edges can be drawn. Simple. If I cannot draw any edges, that means what? Obviously no cycles formed. So if no cycles are formed, that means what? It is serializable. It is serializable, right? Now, if it is so, then how can you deduce the order of working? Why T1 to T2? T1 to T2 will not work. T1 is working on A. T2 and T3 are working on B and C respectively. So T1 to T2, how can you draw an edge? So what is the order? The order can be anything among those three factorials. Suppose if I say T1, then T2, then T3. So T1 will finish all its work on A, T2 will finish all its work on B, and T3 will finish all its work on C. Similarly, if I say T1, T3, T2, then A, C, B, right? So there is no conflict if you go in any order. So all orders are possible. So there is no specific order. All orders are possible. So how many types of order? 3 factorial types of order. Is it clear? This is another type of problem. So 3 types of problem. In the first one, serializability cannot be obtained. In the second one, I have obtained serializability and I have checked that how the serializability can be achieved, right? And the third one, where serializability is achieved, but the order is not specific, you can go in any order of 3 to 3 factorial. Okay. So this is all about your conflict serializability. Any problem given, you can draw the precedence graph and deduce the conclusion whether it is serializable or not. If it is serializable, then what are your like you can say what is the order of working? Okay, conflict serializability boja gelo. Have you understood conflict serializability? Next, we will move to view serializability. So first answer whether you have understood the problems of conflict serializability or not. আরে বুঝতে পারছিস কিনা বল, whether you have understood all these for the last 1.5 hours, whatever is done, have you understood this? Okay, so I have got a couple of yeses. Now we will move to view serializability. Okay, which is a bit complicated, means you have to do many much things. So view serializability is not very much like appreciated, at least not by any of the people who are working, right? So but it is there, so we have to study. So view serializability is what? You have to see, view, and you have to conclude whether it is serializable or not. Okay, so you have to see and conclude. So what is it? Suppose you have a non-serial schedule. Now you have to convert it to the serial schedule. If suppose you have T1, T2, T3, then again that problem remains. You have the bracket of T1, T2, T3, T1, T3, T2, T2, T3, T1, T2, T1, T3, T3, T1, T2, and T3, T2, T1. Okay, so 3 factorial. Now see, in case of view serializability, one non-serial schedule will be given to you and you have to check with everyone that whether it is serializable or not. Suppose one is given and you have deduced this one. Luckily, you are able to prove that this is view serializable. But suppose you are trying with this one, this one, this one, this one, and here you try to prove it as view serializable. So you don't know in which order, if you go, you are able to prove it view serializable. There is no graph, nothing. So you are not sure that in which direction, if you go, you will be able to prove. So you have to just go blindly and search. Okay. So we are not very happy with view serializability, as simple as that. In conflict serializability, we have that like shortcut of precedence graph to comment, but here we don't have to any shortcut, right? So what are the ways to check the view serializability? The first one is, suppose I take an example first. Suppose a serial non-serial schedule, given T1, T2, T1 and T2, suppose. Let us be simple. RAWA, RB, the previous one only, the one with which we have started with. Okay, and suppose I say that an equivalent serial schedule is S1, T1 and T2, where I can serial schedules one after other. Suppose R1 is done first, sorry, T1 is done first. Okay, now I have to check This is not conversion. I have to check whether they are view serializable or not. So the first condition is initial read. What is it? First condition is initial read. The data items that you have, here you have A and B. Who is doing the first read? Who is performing the first read operation in S and S1? Right? So who is doing the first read operation in S and S1 for data items A and B? So if A I take, this is my very first read operation of A in S. This is my very first operation of A in S1. This R1 is done after this. So I am taking the very first one. So initial read means the first read operation on T1. In both cases, it is being done by T1. In both the schedules, the very first read operation on A is done on T1. So in this table, okay. Now in B, the read operation of B very fast, the read operation of B very fast. Before this, no read operation has occurred. So in both the schedules, T1 is doing the read operation of B. If these two are same, then we can say that initial read condition is satisfied. Okay. Very fast read. Initial read is clear. Who is doing the first read operation on a particular data item in both the schedules? Okay, if both are same means this one to this one is not same. This one to this one should be same. These two should be same. So in both the schedules, same transaction is performing the initial read operation. Okay. Next one, final write. Similarly, we will make a table. Data items S1. Final write means the last write operation. The last write operation. So data items are A and B. So who is performing the last write operation of A? This is my last write. After this, do I have any write operation of A? No. Who is my last write? This one. After that, no write operation on A is performing. So in both cases, it is T2, right? Which is doing the last write operation on B. This is my last write operation. After this, nothing is present. So in both the cases, it is T2. Right? Again, if these two are same, both the schedules, same transaction is doing the last write operation on a same data item, then final write constraint is also satisfied. Okay, the transaction who is doing the final write in S must be doing the final write in S1. Okay, if so, then the final write constraint is satisfied. Last operation, intermediate read. Intermediate read. Now see, this read I have already taken, so only this read is remaining. So this read, T2 is doing the read on the value T1 has written. Understand, this is my intermediate read, right? Because this is my initial read I have taken, so this is my intermediate read. Now this read that T2 is doing, this read that your T2 is doing, it is reading the value of T1 that has written some value. That is what it is doing. Here, this is my intermediate read, and it is also reading the value that T1 has written. So what is intermediate read? Read after write on a data item, right? So data item S1, AB. So in A, T2 is following T1. T1 is writing something. T1 is writing on A, then T2 is reading on A, right? So T2 is following T1. Similarly, in S1 also, T2 is reading A that T1 has written. Fine. So both are same. In both cases, the order is same. Similar for B. This is my intermediate read that is being written by T1. Similarly, here also this is my intermediate read and this is. So again, T2 is following T1 in both the cases. Both the cases, right? So this is also satisfying. That means intermediate read is also being satisfied. Fine. So likewise, I can say that this particular these two schedules are view serializable. So how to check view serializability? One non-serial schedule is given, you evolve any one order of the serial schedule. Okay, here it is T1 then T2. You can also do T2 to T1. First you can do T2, then you can do T1. Both are okay. Next you start checking with the three conditions. First condition is initial read. What is initial read? If you have multiple data items, then which transaction is reading the data value for the very first time after initiation? Write in the table and check whether the transaction who is doing the initial read of A in S is same to the initial read instruction of A in S1. If both are same, then initial read constraint is satisfied. Fine, this is initial read. Next one, that is final write. What is final write? When you have multiple data items, the final write means if you have the last write operation of any variable in both the schedules, is it same or not? That is my final write. In both the schedules, whether it is same or not, that is final write. If it is same, then fine, that is satisfied. Last one is intermediate read. Yes, what is intermediate read? If there is any other than initial read, there is any other read operation present in a schedule other than the initial read, then I have to find out an order that the read operation that is being carried out, after which write operation it is being done. After which write operation it is being done. So I have found out the order from this schedule. I have found out that this was my initial read. This was my initial read. So the remaining read is this one. So this is my intermediate read. Now this read is reading the value that this one has written, T1 has written. So T2 is following T1 for A. Now I have to check whether in S1 T2 is following T1 or not. So this is my intermediate read, right? So this one will be reading the value that this one is producing, right? So T2 is again following T1 for A. So that is what I have written. Similar for B, find out what is the other read operation that is present in your schedule other than the initial read. Other than the initial read, right? So if there is any other read operation other than the initial read present, then I have to check the order, order of reading. So after which write operation the read operation is done, I have to find that out. Once I find that out, I will be understanding that whether the order of read operation and write operation are same for a data item in S and S1 or not. If they are same, then intermediate read is satisfied, right? So a non-serial schedule given, you start reducing the order T1, T2, T3, then T2, T1, T3. Likewise, you check the order, and for each one, you have to check the view serializability until and unless you find it true for all three conditions. Suppose T1, T2, T3, this order is satisfying my view serializability. Then fine, I don't have to check for the rest. But suppose this one is not satisfying. So I have to check this one, not satisfying. Then I have to check this one. Suppose at this point, I find that yes, it is view serializable. Okay, or else you have to check the next one, like that. So view serializability is a bit complicated and tedious, not easy like conflict serializability. But if it is asked in the question, you have to do it. Okay. Again, intermediate read, wait. With the instead of initial read, if I have any other read operation present in my schedule, then I have to find out that read operations order. What do you mean by order? Order means this read operation is done after which write. So I am seeing here the read operation to be done by T2 is doing after T1's write. That means what? T2 is following T1. T2 is dependent upon T1. Same thing I have to check here. Here, this is my intermediate read. So after which write it is happening? After this one's write, right? So T2 is following T1 here also. That means for the variable A, intermediate read is okay. Now, what if for the value of B? Here, my intermediate read for B is this one. So it is following this write operation. That means T2 is following T1. Similarly, here, this is my intermediate read. The other one, then initial read. This was my initial read for B. This is my intermediate read. So this is following which one? This one, this write B. Okay, that means T2 is dependent upon T1 also. So for B variable also, intermediate read is satisfied. The order I have to find. Whenever there is any other read operation other than your initial read, then only you have to find out the order of reading. The order of reading, that after which write I am reading. Okay, is it okay? Is it okay? Is it okay? পেরেছো? Yes or no? I'm expecting some answers. Okay, so conflict and view serializability both are clear. Now see, now understand the order. Any problem given to you that check the serializability, if it is not mentioned that you have to follow conflict or view, you will always go for conflict. You will always go for conflict serializability checking. But if it is mentioned that view serializability you have to check, you have to go for view. Now see, the ones which are view serializable are obviously conflict serializable. The ones which are view serializable are always conflict serializable, right? But to find out the vice versa, means if it is conflict serializable and you have to find the view serializability, then it may create a bit problem, means it's a bit tedious, right? So you have to means choose it accordingly, you have to follow it accordingly. Okay. Okay, next we will move towards the PPT where I can show you. Okay, so here very briefly we will just look across that what is there. So when we are calling for serializability, we are talking about the consistency. Fine. Now, for preserving this consistency, when we go for serializability, I have two types, conflict and view. So when we go for conflicting serializability, we have four type of conflict, non-conflict type of instructions. So you can see, if it is a common data item, then read instructions will not conflict and others will conflict. So I have explained that. Now in conflict serializability, we have to find out the serial means the serial equivalent of a non-conflicting instruction. Right, so here you can see the example given. I have also used the same example. Next, we go for the precedence graph checking. So how these edges are being drawn? If you have any conflict instructions, if you give the instructions like conflicting instructions, then you will draw an edge from one to another. Okay, from one to another. So you can see here the conflict serializability. Here you can see if there is any cycle, then there is a chance of, if there is no cycle, there is the chance of serializability. Or if you have the serializability, like you can say the what do you call, the cycle is formed, then serializability cannot be determined, because if there is a cycle, That means there is dependency. Okay. So here is your conflict serializability. Now we will have, you have some terms that you have to understand. First one is the recoverable schedule. The recoverable schedule. Wait. Okay. So in the recoverable schedule, what it means? We know that other than your read write, we have a commit instruction. So here, if you see this particular one, this particular instruction, T8 and T9. So T8 is working on A, T9 is working on A. Now this one is a dependency. T9 is reading the value that T8 is writing. Then I am committing. Fine, I don't have a problem. But T8 has not committed. T8 has not committed. Before that, T9 is committing, right? What if T8 abort? What if T8 abort? If T8 aborts, then T9 has to change its value, but T9 has committed. So how can it change? So if this is my situation where the dependency is present, but the committing, like you can say the series of commitment is not ordered, then we call them as a non-recoverable schedule, right? So if a transaction Tj reads the data item written by Ti, then the commit operation of Ti must appear before the commit operation of Tj. So here only I should have committed to get a recoverable schedule, right? Here only I would have been committed before I start with T9. So if T8 is writing A, after that T9 is reading A. So if T9 has to commit here, then T8 has to commit before. So whenever T9 is starting some operations on A that is dependent upon T8, then T8 should commit first, then T9 will commit. Then only the recovery can be done. Okay, this is recoverable schedule. Next is cascading rollback. Cascading rollback means, see, there are some cascading dependencies. There are some cascading means what? Like staircase. There are some cascading dependencies, right? So if there is a cascading dependency like this, and the T10, that is the first one, no one has committed before the doing cascading dependency, no one has committed. So if T10 is aborting, T10 is determining T11, T10 is determining T11, T11 is determining T12, right? So if T1 is aborting, then T11 has to abort, T12 has to abort, right? So series of aborting of the work leading to undoing of a significant amount of work. T10 is done, T11 is done, T12 is done, but no one has committed. No one has committed, right? Okay, wait, I will share it again. Okay, is it visible now? Cascading rollbacks is visible now. Okay, so here you can see, yes. So here you see T10, then T11, then T12, right? Now T10 is being working, that is right A. Then T11 is reading that value. That means T10 is determining T11, T11 is determining T12, right? So stairs, cascading dependencies are present, but no one is committing themselves. No one is committing themselves, right? So if this is my case and my T10 somehow needs to abort the value, then T11 has to abort, T12 has to abort. So a series of abortion of the work where due to non-commitment, the dependencies are not valid, right? So this is your cascading rollback. If T10 fails to some reason, T11, T12, everyone has to roll back, right? So this is cascading rollback. Very, very important. Cascading rollback. Okay. Next, you have cascadeless schedule. Cascadeless schedule means you have to commit. One transaction has to commit before the next one starts, right? So after T10 is doing 1, 2, 3 operations, then commit will happen. Then T11 will start do 1, 2 operation. Commit will happen. Then T12 will start. Okay. Next is having your view serializability that I have already explained. So 3 rules: initial read, updated read, or you can say intermediate read, and final write. Okay. So after that you have locking. So locking I will not discuss today because that will be again overburdening you. So we will take a few minutes of break and then we will come back with your software engineering problems. Okay, we will come back with the part CPM problems. So those who are present, if you will attend the second session, you want your attendance, then you do not leave. Be here. Okay. So we will just take a 10-15 minutes of break and then we will assemble. Suppose at 11:10. By 11:10, all of us will assemble. Okay, so those who are present, do not leave or else your attendance will be hampered. Okay.
Recording stopped. Recording in progress.
Okay, so let us start now. In this portion of the class, we will do some problems on the software engineering. Last week's slides means which one? In your regular classes you are asking, or in this class? I don't remember I have used any slides in this class. We have done few one or two problems, I believe. Last Sunday I did not take a class. On 15th of April I have taken the class where we have done problems. We did not use any slides. Yes, slack time calculation, all those we had done. So today also we will do similar problem, but different approach of solving them. Okay, so different types of problem we will do, and most importantly, today we will be doing the part chart also. So let us see how much time is there, or means how much we can complete. Now again we will do it using problems only. So first let me do this table. Previous day we had done the problem using the activity names along with their time durations. But today we will be doing it using the edges. Okay, edges. So previous day I have explained to you that activity on the node and activity on the edge. So activity on the node is already done. Today we will be doing the activity on the edges. Nodes also we will do, but first we will do one problem using edges. So the problem can be given it like this: 1 to 2, 1 to 3, 1 to 4, 2 to 5, 3 to 6, 3 to 7, 4 to 7, 5 to 8, 6 to 8, 7 to 9, 8 to 9. Okay, so activities on the edges are given and the time estimate is given. So we have to find the critical path and we have to justify whether our critical path calculation is correct or not. Fine. So first let us draw. See here 1 to 2, 1 to 3, 1 to 4, then 2 to 5. That means before 1 there is nothing. Something to 1 is not there. That means it is starting from 1. Please listen to whatever I am saying while I am doing. So 1 to 2, 1 to 3, 1 to 4 is being done, then 2 to 5, then others. So before 1, nothing is present. Fine. So it starts from 1. Then from 1, I have 2, I have 3, and I have 4. Okay. Achha, from 2 to 5, 3 to 6, 3 to 7. Right? 4 to 7, 5 to 8. 6 to 8. 7 to 9, 8 to 9. That means 9 is my last, 7 to 9 and 8 to 9. This is my diagram. Now let us put the values. 1 to 2 is 5, the time, 6, 3, 5, 7, 10, then 4 to 7 is 4. 5 to 8 is 2, 6 to 8 is 5. 2, 5, 7 to 9 and 8 to 9. 7 to 9 is 6. Okay. So these are your AOE diagram. This is your AOE diagram. Fine. Next, you have to find the critical path and then you have to justify. So how many paths are available? 1, 2, 5, 8, 9. What is the value? If I go via 1, 2, 5, 8, 9, what is the value of the time duration? Just you have to add them. 1, 2, 5, 8, 9. What is the duration? You have to just add them. $16, right? Okay. Next one, let me write 1, 3, 6, 8, 9. What is the value? 1, 3, 6, 8, 9. 1, 3, 6, 8, 9. 22, right? Next path. 1, 3, 7, 9. What is the duration? 1, 3, 7, 9. 1, 3, 7, 9. 1, 3, 7, 9. 27. My God, 26. 1, 3, 7, 9 means what? 6, 10, 6. So how it can be 27, 26? My God. Yes, it is 22. I don't know how you are calculating. Those students who are saying 26, 27, I am really very doubtful. Okay, the last part. 1479. 1479. It is 13. Right? So any other path possible? From the diagram, any other path possible? No? Not any other path is possible? Fine. Now see, what is my empty? Empty is the maximum of all this. 22. Right? Empty is 22. Maximum of all paths, all duration is 22. Now you see, both of the paths, that is path number 2 and path number 3, this one and this one both are producing empty equals to 22. That means what? If I go via this path, or I go via this path, right? My thing is same. Both are my critical path. Now I have to justify, right? I have to justify. That means I have to do the calculation. Okay. Now see, there is a problem. Previous day on the nodes only, you had your numbers, right? The durations. But today on the edges, you are having the numbers. So how can you calculate? Using the edges only we will calculate. For your ease of use, you can just name them. Randomly you can name them. Or else you can write 1-2, 1-3, like that also you can write. There is no problem. Okay, A, B, C, D, suppose E, F, G, H, I, J, K. Okay, randomly I have named, you can name in any way, or else you can write on the left hand side 1-2, 1-3, like that. But I will not write that much, so I have just reduced my work. So edges only, I have named them according to edges. C, F, G, H, I, J, K. Right now I have to justify that both the paths are my critical paths, right? So A, B, C, D, I will start with my ES. So before A, there was nothing. Before E, there is nothing. Before H, there is nothing. So A, E, and H are my beginning edges. So for all of them, the ES will be 0. A, E, and H. Right? So ES is what? Previous than that particular node or edge, something has happened or not. That is my earliest start. So here, before them, nothing was present. A, E, and H are my beginning ones. Before them, nothing was present. That means what? They are my initial ones. So ES equals to 0. Now see, for B, to reach the path B, only A is my path. There is no other path to reach B. So 5, that is the ES of A, is my ES of B. Similar for C, I can reach C only by this 5 plus 5, 10. So I can write this. Only one path present. To reach B and C, only one path via A is present. Now if I say I have to reach D, then one path is this upper path, follow the cursor, and one path is the down path that is following to reach D, these two are my paths. Fine. So this is 5 plus 5, 10, 12, and 16. Okay. If I follow this path, then 6 plus 7, that is 13, plus 5, that is, 6 plus 7, that is 13, plus 5, that is 18. Right? Sorry, not 16. This is 12. 5 plus 5 plus 2. 12. And this one is 7 plus 6, 13, plus 5, 18. So which one is greater? 18. Previously, I have explained how to calculate. Now today I will not again explain. I will just do the calculation. Different type of problems we are doing. Last one, how last one is possible? See here, last one is leading to K, not D. The last one, that is this part, 1, 3, 7, 9. This is not leading to D. D is here and this is leading to K. Right? The path that you have to include that path, right? So it is leading to K, it is not leading to D. So I cannot include that. Okay? Next one, after D, I have E. So E I have already done. Now F. To reach F, I only have E. Okay, so 6. So for F, okay, now to reach to G, to reach to G, I have 6 plus 7, only one path to reach to G. This is my G. So 13. Next, H is already done. So I. Where is my I? This is my I. So to reach I, it is 3, only one path, 3. Next, to reach J. To reach J, I have 6 plus, only 6. To reach J, I have only one path, 1, 2, 3. So 6. So for I, it is 3. For J, it is 6. And for K, to reach K, now see, to reach K, you have 10 plus 6. Okay. Only one path to reach K. K means this point. So 10 plus 6, 16. Okay. So calculation of ES is done. Just check it once. Calculation of ES. Previous paths. If there are previous multiple paths, then you have to take the largest one, right? So ES is done. So once ES is done, EF will be calculated by ES plus duration. So duration, I am just directly writing. For C, it is 2. For D, it is 4. E, it is 6, 7. 4, 6, 7. So 4, 6, 7. Right? G is 5. H is 3. 5, 3, 4. 5, 3, 4. J, K. J is 10 and K is 6. Okay, so this is my EF. Next problematic one, that is LS. LS means I will start from that particular edge and to reach to the end. If I have multiple paths, then I will take the highest. Okay, so just opposite to ES is your LS. To calculate the LS, you have to start from one point and you have to reach to the end point. If you have multiple paths, then the path that is having highest duration, you will take that path. Okay. Now, for A, A is this path. So what is your LS? From A, I can reach to the end only via this path, B, C, and D. So 5 plus 2 plus 4. So 10, 12, 16. So 22 minus 16. Okay, LF accordingly I am writing. LF means LS plus duration. B. B is to reach from B to D, BCD. So 5, 6, 7, 8, 9, 10, 11. Okay. Next C. From C to D, 4 plus 2 equals to 6. Okay. Right. Next D. D is 4. Right? D is only 4. And D is the end. So there is nothing to calculate to the end. Okay. Next E. Now from E, if you want to reach to the end, you have two paths. One is via this, one is via this. So calculate the first one. 6 plus 7, 13, plus 5, 18, plus 4, 22. Then 6 plus 10, 16, plus 6, 22. So anyhow you go, it is 22. So 22 means 0. Okay, and the duration is 6. So 0 plus 6 equals to 6. Are you understanding this? How to reach from E to the end? How to reach from E to the end? You have two paths. One is E, F, G, D, and one is E, J, K. Both paths, if you take, in both the cases, you are having 22, right? So 22 minus 22 is your 0. So for E, your LS is 0. Have you understood? Have you understood? Okay, next for F. For F, to reach to the end is only this one. So 7 plus 4, 5, that is 12 plus 4, that is 16. Seven was the duration. Next G. G to end is 5 plus 4, that is 9. Right? Five. 5 was the duration, yes. G done. Next H. To reach from H is 3 plus 4, 7 plus 6. That is 13. So 22 minus 13. 9. Okay. What was the duration? 3. So next I. From I via this. So 10. 10 means 22 minus 10. Okay. Next one, J. J is this one. So to reach to J, 10 plus 6, 16. Plus 10, 16. Next, 22 minus K is how much? K is 6. Okay. So this is my calculation. Up to this is fine. Next is the slack time. Slack time means LF minus EF. So this is 6, this is 6, this is 6, this is 0, this is 0, this is 0, this is 0, this is 9, this is 9, this is 0, this is 0. So this, this. On my critical path, D, E, F, G, and then J and K. These are on my critical path. Okay. So let me just write it down. D, E, F, G, J, K. So what are the paths possible? E, F, G, D, one path. Another path possible, E, J, K. So all the nodes are covered. So two different paths, E, F, G, D. E, F, G, D. One path I have already done. E, J, K. Already done. So that means the calculation done here and the calculation done here are same. So I have justified that there are two critical paths. Any one of the path you take, it will consume the maximum time, that is 22 weeks or unit, whatever given. Okay, is it clear? Is it clear to everyone? Is it clear? So activity on the node previous day I have done. Today I have done activity using activity on the edge, right? To calculate the CPM, critical path method. Next one that we will do is the program evaluation and review technique. Program evaluation and review technique, part chart. So what is it? Till now, with each activity and each node, we had only one duration, right? So see here, A to B, or I can say the 1 to 2 node, I have 5 weeks of time. So only one timeline was given. But actually in the real case, we have 3 types of timeline. One is the pessimistic time that we call the worst case, or the maximum time that can be consumed is TP. One is the most likely, that is the average time taken to complete a work, that is TM. And one is the optimistic, that is the best case time, that is the minimum time consumed to complete any work. So each activity will have 3 timelines, TP, TM and TO. Okay, nomenclature can be different, but the idea is same. One is the worst case timeline, maximum time consumed. One is the average time consumed, and one is the best case, that is the minimum time consumed. Now using these, we will be calculating the time. We call it as estimated time, T of E. Formula is TP plus 4, sorry, not TP. Optimistic plus 4 of most likely plus pessimistic by 6. Okay, this is my estimated time. This is the most average time by which I can complete. Next, what is my standard deviation of working? Standard deviation means, suppose a timeline is given, whether I can complete within that or not. That is my standard deviation. So standard deviation sigma equals to TP minus TO, always TP will be highest because this is the maximum time. Suppose I say that I can complete this work within 10 days and or maximum I will take 15 days. So TP will be 15 and TO will be 10 by 6. Okay. And if there is any problem, then we will calculate the variance, that is the sigma square, that is TP minus TO by 6. These three formula you have to remember. These three formula you must remember. Okay. Now what type of problem will come? Suppose there is a project where two experts are giving you the judgment, expert A and expert B. The time estimate is given in the TO, TP and TM ratio, right? So expert A is giving you the timeline of 4, 6, 8, and this person is giving you this. So the question is, who is more accurate or more certain? Who is more accurate, who is more certain in giving you the timelines? So what it means, how much variance is there in the calculation I have to calculate, right? So they are giving this timeline, what is my actual variation? So for expert A, my variance is TP minus TO by 6 whole square. So 8 minus 4 by 6 whole square, that is 2 by 3 whole square, that means 4 by 9, which is less than 1, right? And for expert B, this one is 10 minus 4 by 6 whole square, that is 1. 10 minus 4 means 6 by 6 whole square, 1. So this person, expert A, is giving the accuracy lesser than 1. That means the variance or judgment, variance means what? The deviation of A is lesser than the variance of B. That means A is more accurate in the decision. Okay. So terminologies you must understand that where you will apply what. So same project, two experts are doing their judgment. Both are giving some timelines. Now the timelines that are given, based on this you have to judge that how much accurate is your result, is the expert's result, right? So for that, accuracy, how we will determine? Accuracy we will determine by variance. Variance means the change or the range, whatever you call. So for expert A, my variance is less than 1. And for expert B, it is equals to 1. That means expert A is more accurate. So that is what I have written. This is my answer. Okay. Next one, next problem that we will do. Let us do it in a new page. Question number 2, suppose the activity, I'm writing in short, TO, TM, TP. And from this you have to calculate the TO, sorry, TE, not TE. Okay. 1 to 2, 3, 6, 9, 1 to 6, 2, 5, 8, 2 to 3, 6, 12, 18, 2 to 4, 4, 5, 6, 3 to 5, 8, 11, 14, 4 to 5, 3, 7, 11, 6 to 7, 3, 9, 15, 5 to 8, 2, 4, 6, 7 to 8, 18. Okay. TE is what? TO plus 4 TM plus TP by 6. Okay. So values you will calculate on your own. I am not spending time for calculation. So I'm just directly calculating it and writing it here. 11, 7, 9, 4. Okay, always it will not be this one and this one will always not be same. See the last case. Okay, so do not blindly write whatever is your TM is your TE. It's not same always. Okay, I hope you understand. TM and TE, they are always not same. Fine. Now you have to, what is your question? You have to calculate the project time. Project time means the critical time. Okay, project time means the critical time, the variance and the standard deviation. Okay, so you have to calculate the critical path, then only you can calculate the variance of that path and standard deviation of that path. Only one task standard deviation you will not calculate, obviously. Okay, so let us draw. So 1 is the starting point. Before 1 nothing is there, so 1 to 2, 1 to 6, 1 to 2, 1 to 6, then 2 to 3, 2 to 4, fine, then 3 to 5, 4 to 5, then 6 to 7, 5 to 8, 5 to 8 and 6 to 7 to 8. Okay, let me write down the numbers. Now see, the numbers that you will write on the edges will be your TE. Okay, the numbers that you will write up to now, whatever you are writing were the durations given, but here your duration is not given directly. It is given in the form of TP, TO and TM. So you have to calculate the TE and you have to write that number. Okay. So let me write these numbers. 6, 12, 11, 1 to 6 is 5, 2 to 4 is 5, 4 to 5 is 7, is 4, is 15, and this is 9. 9 and 15. Okay. Now, if I follow 1, 2, 3, 5, 8, then my value is 18, 19, 29, 33. If I follow 1, 2, 4, 5, 8, 6, 5, 11, 11, 18, 22. If I follow 1, 6, 7, 8, 29. So which is highest? This one. So this one is my project time. Here they have not asked for parameter. They have not asked for parameter, so I am not calculating. Directly from this, the critical path is the highest time duration path. So this is my critical path. So which are my critical activities? One to two, two to three, three to five, five to eight. Right? These are my critical activities. So for them, my value of TO, TM, TP, I have to calculate the variance, right? So critical first question is done. Project time 33 weeks. Okay, weeks, if suppose these are given in weeks. So 33 weeks, fine. Next one, I have to calculate the variance. So for variance and standard deviation both. So for that, I require the value of TO, TP, and TM. So what are my 1 to 2, 2 to 3? So 1 to 2 is 3, 6, 9, and 6, 12, 18. 3, 6, 9, 6, 12, 18. Then 3 to 5 is 8, 11, 14. And 5 to 8 is 2, 4, 6. Right? So from here, first I will calculate the range. That is TP minus TO. So 6, 12, 6, 4. Right? Next, I will calculate the deviation. Okay. So it is 1, 2, 1, 2 by 3. Next, I will calculate variance 1, 4, 1, 4 by 9, 4 by 9. Fine. So up to this is okay. Now I have to calculate it for the total. Right. So this is for individual parts I have calculated. Now I will be summing them up. So the total variance of the critical path equals to summation of the task on the critical path. So 1 plus 4 plus 1 plus 4 by 9, or you can calculate it. So it is 58 by 9, right? And from the standard deviation, this is your variance. If you calculate the standard deviation, that is root over 58 by 9, approximately 2.54 weeks. Okay, so the timeline that will be given, it will deviate by 2.54 weeks. So how to do the calculation? I'm just repeating it once quickly. Problem will be given like this and question accordingly. So according to each activity, you have to first calculate the estimated time using the formula TO plus 4TM plus TP by 6. So do the calculation. Do not blindly write TM equals to TE. That is not correct. The answer can be different. Then you draw the diagram using the TE that you have calculated. Using this TE, you find out how many paths are possible. From that path, find out the critical path having highest duration. Here it is 33, having 1, 2, 3, 5, 8, these numbers. So for each of them, take the values, calculate the TP minus TO, and accordingly the standard deviation and the variance. Using the variance, calculate the total variance of the critical path. Total variance of the critical path. Fine. After this, take a root over and your standard deviation will be found. Okay. So this is how different type of problems you may have. So I'm just trying to explain one type each. So today we have done 3 problems. One is the AOE problem. One is what is part chart and how to solve this expert. If two experts are giving a judgment, then how to solve it. That then using this, I have calculated using the part chart. We have calculated this one, that is by taking the TE, how to calculate the final variance. Okay. So this is how you have to solve. There are other types also, but today time is not there to do that much. So next day we will again proceed. Full form of part is program evaluation and review technique. Program evaluation and review technique. Okay, so next day we will be doing the transaction lockings, types of lock, how to acquire, not acquire, how to release those things. And we will do the rest of your part chart and so on. Okay. So today we are done for these things. Fine. So if you have any question, you may ask. Okay. So if you don't have any more questions, then we can break the session. Thank you. See you in the next class.